So welcome everyone. We'll wait a few seconds for the audience to join us. And we are going to start promptly. Oh, it's 4 o'clock already. So let me start the introductions. Thank you for joining the sessions of the VSET. And today we have a pleasure of having Ben Brooks from Chicago. Ben is going to talk about on the structure of informationally robust optimal auctions. This is joint work with Songzi, who is also with us today. And our guest panelist today is Marzena Rostek. Welcome all. Just to remind everyone, the format of the seminars is as follows. We have a 60-minute presentations with time for interim questions from the panelist, Marzena. But also we encourage the audience to participate. So please post comments and questions and hot takes in the chat. And Songzi will have an eye on that and might ask live as well. There will be an opportunity to ask questions live at the end in the Q&A sessions. And finally, if something is very important or you have a clarifying questions, you can also unmute yourself and ask questions live. And the talk is recorded. After the talk, after the Q&A sessions, we'll meet in the Virtual Chairs Academic Metaverse. It's a different platform, not on Zoom. This is going to be an informal chat. If you have a few minutes and want to have an informal chat, please join us. And the link is going to be in the chat in a moment. Before I hand over to Ben, let me invite you to our next seminar. Ying Chen from Johns Hopkins will present technology investment under power fluctuations next week, next Thursday. Guest panelists Salvatore Nunari and Roger Lagunov. And you can find more information on our website and by following us on Twitter. And thank you, Ben, for joining and accepting our invitations. The screen is yours.
Okay. Well, thank you very much for inviting me. And I'm going to present this paper, this joint work with Songzi at UCSD. And slight change of title. Oh, can you all see this if I? Oh, it seems that the screen is frozen. Let me try this again. Zoom share. Okay, now it's working. Okay, slight change of title to mechanisms rather than auctions, reflecting our great ambitions or delusions of grandeur, depending on your perspective. So here is the problem that we're working on. It's really the standard Bayesian mechanism design problem. So you're a mechanism designer and you have some welfare criterion W, and there's a set of agents, and those agents have private information about payoff relevant states, and what the agent, and you'd like to know as the mechanism designer what the agents know, so that you can use their information to guide your choice of whatever alternative is under the control of the mechanism designer. In the standard model, it's assumed that the mechanism designer knows the form of the agent's information about payoff relevant states, which is generally modeled as a type space in the sense of Harsanyi, or we're going to use the equivalent terminology of an information structure. And our point of departure from the standard model is that instead of assuming that the mechanism designer knows exactly what the agent's information is, actually, there's uncertainty about the agent's information. It's Knightian uncertainty, so it can't be quantified in terms of a Bayesian prior over the type space that describes the agent's higher beliefs. And why are we doing this? Well, this is meant to be a sort of repair some deficiencies in this, as we see them in the standard model. So we're especially interested in settings where there could be complicated interdependence in signals or correlation in signals of the agents. And in those kinds of settings, the standard model, we would argue, has not given us great insights about what kinds of mechanisms to use. For example, in the auction design setting, when there's correlation in agent signals, the standard model generally predicts that the auction designer should try to extract agents' beliefs by having them make bets about other agents' signals in the style of Kramer and McLean mechanisms. And while those mechanisms would perform well according to Bayesian welfare criterion for those information structures for which they're designed, they lean very heavily on this assumption that the mechanism designer knows the true correlation structure of the agent signals, knows what their higher order beliefs are. And we would argue that in a lot of practical settings, the mechanism designer does not know that information to such a degree to really be able to calibrate those bets. So we're going to take a max-min approach instead and kind of endogenize the information structure. And we think of that as really a heuristic that's going to guide us to interesting new designs of mechanisms where we can say something about how those mechanisms will perform in lots of environments, even though these mechanisms may not be optimal for the true environment. So, right. Oh, I guess I have one more line on the slide. The question is, what mechanism should you run? What mechanism should you run? And that's what we're going to try to provide an answer to with this max-min heuristic. So in particular, we're going to look for mechanisms that have good guarantees, in fact, the best possible guarantees for performance uniformly across all information structures and equilibria as well. Actually, we're going to throw that in, that our mechanism designer is going to be concerned that a bad equilibrium might be played. And so they want the mechanism to perform well in all equilibria. Okay, and again, this is a heuristic meant to guide us to new and interesting mechanisms. They may not be exactly optimal mechanisms given what a designer knows about the informational environment, but they're a natural starting point or a benchmark that could be improved upon if the mechanism designer knows more. Okay, so our kind of methodology is actually to study a pair of optimization problems. So these are holding fixed a distribution of the payoff relevant states. So the first problem is kind of what I just described to you. We call this maximizing the guarantee, or the max-G program. So this is the max overall mechanisms of the min over information structures and equilibria of this expected welfare criterion. So this is identifying mechanisms that provide the best lower bound on welfare across all information structures and equilibria. A kind of dual to that program is what we'll call the minimum potential program. So this is if we were to minimize over information structures, the maximum over mechanisms and equilibria of expected welfare. So why do we call this min potential? Well, for a given information structure, the kind of potential for how well the mechanism designer could do is the maximum over mechanisms and equilibria of W. So the solutions to this problem are minimizing that potential. So these two programs are going to bound how well the mechanism designer could do uniformly across all information structures and equilibria for different assumptions about, first of all, whether or not the mechanism can condition directly on the information structure, and second, whether which equilibrium is going to be played. Is it the designer's preferred equilibrium or the designer's worst equilibrium? So these are the programs that we study, and we have. Oh, go ahead.
So the solution concept you're interested in or you're employing is equilibrium, and I mean that's attractive for most of us, but sometimes people are interested in weaker solution concepts. Are these ideas going to carry over to say rationalizability based concepts to the extent that we're interested in fixed point characterization?
It's a good question. It's a good question, and the answer for now is we don't really know. It is true that we're using Bayes-Nash equilibrium, and Songzi and I actually have started thinking about generalizing this to weaker solution concepts. Go ahead.
The equilibrium is the holy grail, right? If it's really the first best, but I'm sort of thinking ahead a little bit, and sometimes people are interested in rationalizability or other weaker solution concepts. So you're saying it's still an open problem.
Exactly. So in previous work, what we've done is we've studied these programs, first in the context of revenue maximization and auctions. We also have work that's studying social welfare or total surplus maximization in bilateral trade. And in that work, we've shown constructively that these two programs have the same value. And there's lots of structure at the saddle points. And in particular, and what do I mean by a saddle point? I mean, there's lots of structure in the guarantee maximizing mechanisms and the potential minimizing information structures. And that leads to relatively simple, we think of as simple forms for the guarantee maximizing mechanisms. And we think they are actually serious proposals for mechanisms to run. And the potential minimizing information structures are not that exotic, which kind of suggests that actually these are not extraordinary worst cases that these guarantee maximizing mechanisms are protecting against. Okay, so for example, in the case of revenue maximization and auctions, the guarantee maximizing mechanisms are what we call proportional auctions, where there's an aggregate supply rule and a pricing rule, and the aggregate supply and the pricing rule just depend on the sum of the agent's bids. So bids end up being positive real numbers, and the total amount of the goods supplied and the price just depends on the sum of the bids. And then individual bidders get an allocation, get a probability of receiving the good that's proportional to their bid. So it seems like it was, to us at least, a surprisingly simple functional form, given the range and potentially complex environments in which and equilibria in which we can lower bound welfare for this mechanism. And it seems like something that you could actually implement in a variety of contexts. Okay, so that's part of the motivation for why we think these programs are worth studying in general, is that these programs lead to interesting new forms of mechanisms. Now, in proving that our constructed solutions are actually solutions for these max G and min P problems, what we actually show is that they are solutions to a pair of restricted bounding programs that bound the value of the max G and the min P programs. And these bounding programs are actually linear programs. So in this paper, so a large part of the theory is about studying those bounding programs. Those bounding programs are much more analytically tractable, and they're what guide us to the solutions. So in this paper, what we do is characterize these bounding linear programs for a much more general class of mechanism design problems than what we've looked at previously. And the logic of these bounding programs tells us a lot about the structure of guarantee maximizing mechanisms and potential minimizing information structures. In particular, like what makes a mechanism informationally robust is elucidated by these bounding programs. So in particular, the bounding program for the potential minimization problem reduces to, or is effectively computing the information structure that minimizes an expected highest, what we call informational virtual objective. And this is a generalization of the classic virtual value. So there's some social welfare that would be generated, or there's some welfare from the designer's perspective that would be generated by an outcome. And then there's a cost, which is given by information rents that come from local deviations. And that's exactly what this informational virtual objective embodies. So in the auction context, it would reduce to just maximizing or minimizing an expected highest virtual value. On the other side, for the guarantee maximization problem, guarantee maximizing mechanisms maximize an expected lowest strategic virtual objective, which is kind of the dual counterpart of the informational virtual objective, and is a new concept that has arisen in these papers, in this paper in particular. So that's the bounding programs, and they're bounds for a very general class of mechanism design problems. A $1 million question is whether these bounds are tight, and are they actually going to, if you solve the bounding programs, will you necessarily get solutions to the original max G min P problems? And, as I said before, in various papers, we've shown that these bounds are tight constructively. A new result in this paper is to show that the bounds are tight non-constructively for a general class of auction design problems where revenue maximization is the objective. And here, the value is really to give us a better conceptual understanding of why these two bounding programs should have the same value. And in particular, they're kind of almost a dual pair to one another. And there are subtle differences between them that make them not exactly a dual pair, but at least in certain situations, in particular revenue maximization in auctions, that subtle difference is not going to materially affect the value of the programs.
Ben?
Yes.
But when the bounds are not tight, your approach still allows us to evaluate how far we are, right? And in fact, it's sometimes more interesting in some applications that may be even more interesting than looking at the mechanism at the subtle point.
I agree. I mean, of course, whether or not they're useful depends on how far you are. Or,
right. No, absolutely. But I mean, being able to do it is useful. I have a more general question. So in your prior work with Songzi, in your first Econometrica paper with Songzi, and in your BBM paper, you looked at more specific applications. Here, you're going to show us that you can formulate the restricted program much more generally. I mean, you're going to achieve a new level of generality we haven't seen before. So two questions. What was the key insight that allowed you to see that the structure is there, that this formulation is possible? And the second question, can you be a little bit more specific about the new problems we can handle? Right? New applications.
Maybe can we come back to that question after?
Absolutely, yes. Let's do it.
Model?
Yes.
But those are great questions. Yeah, excellent. Okay. And then lastly, in this paper, we do solve for guarantee maximizing auctions in some new settings, but the main point of this paper is methodological. Okay, so the plan for the talk is to derive the general bounds, talk about why they're tight in revenue maximization and auctions, and then in the last few minutes, I'll show you some examples. Okay, and then there's a lot of related research on robust mechanism design, especially on classical Bayesian mechanism design, and also on information design, because we're really solving two problems simultaneously. One is a mechanism design problem of computing this guarantee maximizing mechanism, and the other is the information design problem of finding the worst informational environment for the designer. Okay, so here is the model. There are n agents. There's a finite number of possible payoff relevant states, theta. There is a known and fixed prior over the states called mu. And the designer is in control of an outcome, x. And x, really you want to think of that as being a subset of some convex polytope in RK. But some things don't rely on exactly what we say the outcome is. And then we also have preferences for each of the agents that'll be denoted by UI, that depends on the outcome that gets implemented and the payoff relevant state. We want to model a participation constraint for the agents. And the way we're going to express that is the agents have an outside option. Each agent I has an outside option. And if they exercise it and the state is theta, then they're going to get this U lower bar I of theta. And, of course, whether or not they want to exercise it may depend on their beliefs about theta. And we haven't specified their beliefs yet. But this is at least saying what their payoffs would be if they exercise the outside option. And then finally, there are preferences from the designer, which are this little w. So a mechanism is just a pair of a set of actions for each agent, and then a function G that maps action profiles into an outcome. Okay. Oh, I should mention that, why am I saying RK? Well, we're basically going to assume that U is linear in X in a few slides. So that's why we're looking at X's that are in Euclidean space. Okay. So here's the connection to participation. We want to model participation constraints in sort of a flexible way. And when we don't know what the information is and we don't know what equilibrium is being played. So the way we're going to force the designer to respect the agent's participation constraints is that we're only going to allow for mechanisms that satisfy this condition that we call participation security. Participation security says that for every player, there is an action that we'll call 0. And this is like your safe word. And if you say your safe word, then you're guaranteed to get a payoff of at least the outside option, no matter what actions others take and no matter what the state is. Okay, so this is sort of a little bit weaker than an ex post participation constraint because, you know, it may be that an agent chooses not to take this action 0 in equilibrium, in which case maybe they will sometimes get a lower payoff, but they always have the option of taking this action 0. So it must mean that whatever their beliefs are, they expect to be getting a higher payoff than if they did exercise their outside option. Okay. And then M is the set of participation secure mechanisms. For technical reasons, we're going to restrict attention to finite mechanisms, so only finite action spaces. And then an information structure consists of, for every agent, a finite set of signals. And then there's a joint distribution over the agent's signal profiles and the state, such that the marginal of this joint distribution on the state is mu. So we're going to range over these information structures, but as we range over them, we're holding fixed fundamentals, you know, the distribution of the payoff relevant state. Okay. So given a pair of a mechanism and an information structure, you know, that's a Bayesian game. Agents have behavioral strategies that map their signals into distributions over actions. Bayes-Nash equilibrium is defined in the usual way. And the induced payoffs from a strategy profile are just going to, you know, the expectation of your individual payoff, where the expectation is over states, signals, and actions. So the distribution of the signals and the states is given by the information structure, and then the conditional distribution of actions is given by the agent strategies. So here are the guarantee maximization and potential minimization programs. For the former is the soup over all mechanisms, inf over information structures, inf over Bayes-Nash equilibria of the expected payoff of the designer. And for potential minimization, we're going to first take the inf over information structures, soup over mechanisms and equilibria of the expected payoff. So this is the min potential. Okay. So the next order of business is to describe these bounding programs. And then I'm going to give you a theorem that says that these are in fact bounding programs. Okay, but I'm sort of going to build up to the theorem with the derivation so that you understand where the bounding programs come from. And it's kind of a three-step process. So first we're going to simplify things using a pair of revelation principles. And then we're going to take a Lagrangian relaxation where we replace equilibrium constraints with by putting them into the objective with Lagrange multipliers. And then a judicious choice of these Lagrange multipliers is going to make these two programs look kind of similar. And those are the bounding programs that we end up with at the end. Okay, so first, how can we use the revelation principle to our advantage here? Well, let's start with the potential minimization problem, where we're minimizing over information, max over mechanisms, max over equilibrium. Now fix an information structure in that outer program, and in the outer infimum, then the inner problem looks like this. This is just the classic Bayesian mechanism design problem with a fixed information structure, with one subtle difference, which is that we're requiring this participation security condition on the mechanism rather than the usual interim participation constraints. Okay, but we could always relax interim participation is a relaxation of participation security. It's implied by participation security. So we could make the designer's problem easier and increase this soup by just letting them choose any mechanism that satisfies interim participation. And then the revelation principle applies, and we know that it's without loss to restrict attention to incentive compatible and individually rational direct mechanisms. And so what is a direct mechanism? A direct mechanism is one where the actions are just equal to signals. And G is such that truthful reporting of your signal is in equilibrium. So there are going to be there are truth-telling constraints, and then there are interim participation constraints. These are the truth-telling constraints, and I'm going to attach. So this is for if you're agent I type SI misreporting SI prime, that has to lower your payoff, and I'm going to call alpha I of SI prime the multiplier on that constraint, and that's just this. If I take the expectation over other signals and over the state, then the difference in my payoff between when I report my true type SI versus SI prime has to be positive. I have to be better off with my true report. And then similarly, we're going to attach a multiplier beta I of SI to the interim participation constraint of agent I type SI, which is just saying that the interim expectation of your utility under the mechanism for truthful reporting has to be greater than what you'd get from the outside option. Okay.
Can I ask a quick question on the previous? I mean, maybe it's too. So it seems that you implied if you didn't relax it and if you had participation secure instead, then the mechanism is, so the revelation principle doesn't necessarily apply. Is that right?
Right, because I have this extra action floating around, the participation secure action, the safe word, which doesn't correspond to any type. So it would not literally be true that I could just choose actions equal to signals. I have to have that extra action in there.
I see.
But really, I don't think it matters. It's not a strict relaxation, at least in the cases where the bounds are tight. That's a proof that this is not a strict relaxation, actually.
Okay. Anyway, okay, thanks.
Okay, so for the max guarantee problem, if you fix a mechanism in the outer problem, then the inner problem is just infimum over information and Bayes-Nash equilibria. And there's another revelation principle for information design that you could use here. This program is equivalent to minimizing W over all Bayes correlated equilibria, which are information structures where signals are equal to actions, are identified with actions. And so a signal is basically a recommended action. And there's an equilibrium in which the agents obey their recommendations. So you're in equilibrium, your action is equal to your signal. This should be A minus I in here. At any rate, so there are now obedience constraints that say when you're recommended to play AI by the information structure, you don't want to deviate to AI prime, okay, given that others are following their recommendations. So this is similar to the truthful reporting constraint from the previous slide, and I'm in fact going to use the same alpha I to denote it as a multiplier, with the notation being slightly overloaded, that when it's multiplier and obedience, we're going to use A's as the arguments rather than S's. Okay, so now what we've done is, for those two problems, we've replaced the inner problems with using the revelation principle with either maximization over direct mechanisms or minimization over Bayes correlated equilibria. And these are the resulting programs. I don't expect people to follow along with detailed formulas too much in real time necessarily, but I'm going to tell you what is important about these formulas. So for min P, now we have minimization over information. So suppose we fix a set of signals. Okay, we're going to look at sort of a constrained version of the min P problem where we've fixed a particular set of signals, and then nature is now just choosing sigma. And then the designer chooses the mechanism, the direct mechanism, subject to maximize an expected welfare criterion, subject to IC and IR. And rather than incorporating those as constraints, we're now going to put them into the objective and formulate a Lagrangian, where we just have a weighted sum of the participation constraints with the corresponding Lagrange multipliers, and also add in the participation constraints with the corresponding Lagrange multipliers. So this is a Lagrangian relaxation of the min-p problem. Okay, this is now an upper bound on the min-p problem. Why is it an upper bound? Well, because we're adding something positive, the non-negative Lagrange multiplier, times something positive, the change in utility from a misreport. And similarly, we're adding a positive multiplier in participation times the positive difference between equilibrium payoffs and the outside option. Okay, so that's why this is an upper bound on the seller's, or on the designer's objective. Correspondingly, in the max G problem, if we fix a set of actions, then now we've got maximization over participation secure mechanisms for that set of actions, where implicitly we have a little zero in here. And now minimization over base correlated equilibria. We're going to take a Lagrangian relaxation of that problem as well, where now we have minimizing the expected welfare of the designer. And then to get a lower bound, we're going to subtract off something non-negative, which is now subtracting off the non-negative multiplier on obedience times the difference in payoff from a misreport. Okay, so this is, go ahead.
Sorry, I have a couple of quick questions. So first of all, it seems like there's not a symmetry here because you have incentive compatibility and participation constraints on the one hand, and you have obedience constraints only in the other. So I'm obviously missing something, but there seems to be an asymmetry. And the other question is, are you doing this with lower bound on max G? It seems like you are, right? Lower bound on max G has to be a lower bound. You're not looking for an upper bound on max G.
Exactly.
Right.
Easy arguments from zero-sum games will tell you that min P is greater than max G. And so what we're trying to do is find an upper bound on min P and a lower bound on max G.
Right.
Then we're going to show that those bounds coincide, which is going to force min P and max G to coincide.
Right.
So you're exactly right that we're looking for a lower bound on max G.
But what I'm missing is that thing that you said in a second, which is zero-sum game argument. I suppose that's the thing that.
Well, okay. Look at
go on.
In the min potential problem. Okay.
Mm-hmm.
The designer, for whatever information structure nature picks, the designer could always use one of those guarantee maximizing mechanisms. And then even in the worst equilibrium, their payoff is going to be greater than the value of the max G problem.
Okay.
Right? So in the best equilibrium, you have to be doing even better. So that's the sense in which it's the usual zero-sum game argument. The maximizer always has the option to use whatever is their max min action, even when the minimizer goes first, and get at least the payoff that they would get when they went first. But to your first question, so your first question was about all the asymmetries between these problems. And there are three asymmetries, okay, that I should highlight. First asymmetry, order of moves is different. Min max versus max min. Second difference, here participation constraints are in the objective. Here they're in this restriction to participation secure mechanisms. Okay. Third difference, here we wanted an upper bound, and that's why we're adding things that are non-negative. Here we wanted a lower bound, and that's why we're subtracting off things that are non-negative. Okay. Now this difference, I'm not going to get rid of, but the other two, I'm going to argue we can get rid of. And then the only difference between the two programs is in how we model the participation constraint.
Can I try and ask a question to get a handle on this? So, and if it's silly, just ignore it. So I'm just trying to think of this as an auction thing. So then the first problem, as you mentioned, if for a given sigma is just like a Kramer-MacLean problem, right? In the auction setting. So it will be some kind of side bets, and I'm going to extract all surplus or something like that.
Well, it depends on what the information structure is. I mean, I would say that it's just the standard classical Bayesian auction design problem of Meyerson 1981, when there are independent signals or you know,
right. And I was just going to say the worst case would be the independent signal case then. Like if it's correlated, we know we can extract everything, and somehow the worst case will be the independent.
That intuition is exactly correct.
Okay.
And that happens whenever there's transferable utility, basically. Whenever this W has some component of transferable utility between the agents and the designer, that's going to force you to independent signals.
Okay.
If I have time, I'll come back to that later in the talk.
Okay, thank you.
Right. Okay. So now the question is kind of what are multipliers? What are the optimal multipliers? I mean, that's a big question, right? Here I've just said whatever the multipliers are, just throw them in. But we want to pick multipliers that are close to optimal in order for these Lagrangian relaxations to be tight. But in addition, you know, under the sort of operating under this ansatz that these two programs should have a similar value, we should be choosing multipliers so that these two programs look similar. Okay. Now I'm going to argue that there is a particular choice of multipliers that will result in fairly similar looking Lagrangians. And what is that? They're local, they correspond to binding local constraints. So let me, you know, until now, the particular labels of the actions hasn't mattered. They're just some abstract finite set. But I'm going to give them labels. And in particular, I'm going to make them be a grid in increments of 1 over L going up to some integer L. So this has L squared plus 1 points in the grid. And I'm going to choose in the min P problem, I'm going to make the multiplier equal to L if the multiplier corresponds to a downward deviation, or if it's the participation constraint of the type 0. And then, so this sort of corresponds to binding downward deviations and a binding participation constraint only for the lowest type, which is sort of classically what you get in the auction design problem. And then for the min G problem, I'm going to pick binding local upwards obedience constraints. And all the other multipliers are going to be 0, meaning we're dropping all of the other constraints essentially. So if you do that, then this is the program that these are the programs that you'll obtain, which again, this is a god-awful mess of mathematical notation. But the important thing is now we just have in the Lagrangian differences from local downward deviations in the min P problem with a weight of L, and and then the participation constraint of the lowest type with a weight L. And in the max G problem, now we just have local upward deviations with a weight L. Okay. Now, why local down here but local up in the second one? Well, it's about the difference in the sign. It's about the difference in the sign, because now if I pull the difference in sign in here, I can make everything positive. And now what does this look like up here? This is like a local upward derivative. This is like a discrete upward derivative of the utility of agent I with respect to their action. And up here, I have a local downward derivative of the utility of agent I with respect to their action. So now these two terms look quite similar, except that I've changed the direction in which I'm taking a local derivative. Am I taking a local derivative going up or going down? Okay. And let me introduce a little discrete differential notation to summarize that operation. Now, the min potential bounding program involves local downward derivatives, and this one involves local upward derivatives. Okay, where it's implicit that if you're the lowest type, then this local downward derivative is with respect to the outside option. Okay. Now I'm almost done. So now I've gotten rid of a lot of the differences between those two programs. I've gotten rid of the sign difference, or sort of replaced it with a difference in the direction of local derivatives. And then still participation is implicit in here for the lowest type, whereas it's over here for the max G problem, for the max G bound. Okay. But at any rate, these are the programs that we've arrived at. And I still have a difference in order of moves. Okay. But now if I further assume that this utilities are all linear in X and W is linear in X, and that X is a convex polytope, as I suggested I would when I was giving you the model. Well, now the minimax theorem applies to this problem, and I can reverse the order of moves so that now actually that's no longer a difference either. Okay. And then a little bit further simplification. Oh, okay. So one more layer of simplification. Now, if you are, let's see. If you're nature and you're solving this problem, nature can't change the distribution of theta. It has to be the mu that we fixed at the beginning, right? All nature can control is the conditional distribution of S given theta, right? So what are you going to do if you're nature faced with this problem and you move second? Well, you'll just put probability, given theta, you'll just put probability 1 on whichever S minimizes this term. And similarly down here, nature can't change the distribution of theta. So nature's minimization problem, the solution is just going to reduce to putting probability 1 given theta on whatever is the action profile that minimizes this term. So let me just solve out nature's action and rewrite the problem as just max over G of min over S of this expression right here, max over G that's participation secure, min over actions of the corresponding expression. Okay. So this is the final form of the bounding programs, basically. This min P prime of L is an upper bound on min P, on the restricted version of min P, where nature is allowed to use L squared plus 1 signals, basically. And this max G prime of L program is a lower bound on how well the mechanism designer can do when they're allowed to use L squared plus 1 actions. Okay. And in both cases, these programs have the form of the designer choosing the mechanism to maximize an expected minimum, what we call strategic virtual objective. That's this term in brackets. And it's the designer's welfare criterion plus this strategic adjustment, which takes into account the local incentives or the incentives of the agents. And the difference between the two programs is, again, how participation is modeled, and also whether or not the strategic adjustment is in terms of local upward deviations or local downward deviations. Okay. Now, I said at the beginning of the talk that one interpretation of the guarantee maximizing mechanisms was in terms of maximizing an expected lowest strategic virtual objective, and that's exactly what we've gotten out of this slide. I also said that potential minimizing information minimizes an expected highest informational virtual objective. Now, back here, when we sort of reversed the order of the moves, that was when we were moving towards solving out the information. But at that stage, I could have not reversed the order of moves, and instead we could have worked a little bit more with this sort of dual of the upper bound on the, or maybe it should be viewed as the primal for the bounding program for min P. So this is what we had before we reversed the order of moves. And instead of solving out nature's action, we could solve out the designer's action, basically using this in the same way. Why is that? Well, in this problem, a given choice of g of s is going to impact multiple terms in this expression because of this derivative differential operator here. But what I can do is integrate this or sum this term by parts. And here you just have to sort of follow me with a leap of faith that we've done the summation by parts formula correctly. But if you do that, you can replace differences in signals applied to utilities with differences in signals applied to the distribution. So that's how we're doing the summation by parts, to move this difference operator off of the u and onto the sigma. Okay, and if we do that, then this is an equivalent expression where, again, now we have a discrete upward derivative operator applied to the signal rather than a discrete downward derivative operator applied to the utility. But this is the same expression that we had before. And now we can solve out G, right? Because the designer is choosing G, but the designer, what is the optimal thing to choose? The designer should just choose whichever is the outcome, G of S, that minimizes this expression given S, right? That's what's going to be optimal for the mechanism designer. So we can just solve that out. And now the problem, the bounding program for min P has been reduced to minimizing over information structures of the expectation over signals of the maximum over outcomes of this term in here. And this is what we called the informational virtual objective. Now, this is the object that in the auction design setting reduces to the virtual value. And if we have time, I'll try to convince you of that when we get to the special case of auctions. Okay, so now I'm ready to give you a theorem at long last. So if I, for a given program P, I'm going to let W of P be the optimal value of that program. And here's our theorem. For any L, the bounding program for min P with L squared plus 1 signals has a value that's greater than min P, which has a value that's greater than max G, which has a value that's greater than the bounding program for max G with L squared plus 1 actions. And then, moreover, if G solves the max G prime of L bounding program, then the designer's payoff from using that mechanism is at least the value of that program in any information structure in equilibrium. So in other words, not only are we getting a lower bound on the value of the program, but that bounding methodology is giving a lower bound on the performance of G in any information structure in equilibrium. And similarly, if you have a sigma, an information structure that solves the dual of the min P prime of L upper bounding program for min P, then the designer's payoff is at most the value of the bounding program in any mechanism, participation secure mechanism in equilibrium. So in other words, these bounding programs are not just bounding the value, they're giving us mechanisms and information structures that attain those bounds, okay, uniformly across mechanisms in equilibrium or information structures in equilibrium. And in the case where these bounds end up being tight, when L is sufficiently large, these bounding programs are going to be giving us approximately guarantee maximizing mechanisms and approximately potential minimizing information structures. Okay. So that's the theorem. And the big question is really, when are these bounds tight? And, intuitively, this is going to be the case when the solutions are sufficiently smooth that local upward and local downward derivatives coincide. And also, this difference in how we model participation constraints between interim participation and participation security, when that doesn't matter either. And of course, it's always possible to show constructively that the bounds are tight by just exhibiting solutions to the bounding programs that have the same value or approximately the same value as L goes to infinity. And we've done that in various contexts. We've just shown, we've constructed solutions to those bounding programs that have close to the same value, therefore the programs are tight. But we're also interested in understanding kind of non-constructively when are these bounds going to be tight. And in this paper, we've done that for kind of general auction design problems where revenue maximization is the objective. So in that setting,
excuse me. Hi. So more generally, how would we go about finding these solutions and computing them? I understand we can use your restricted program to compute approximate mechanisms and information structures, and then deduce the right functional forms. Would this be the right approach, or?
Well, good. So these are, I didn't emphasize this again just now, but I said it in the introduction that these are linear programs for any L. So, you know, you can study solutions of those linear programs either analytically or computationally. So what Songzi and I do is often is a little back and forth, actually, between analytical and computational approaches. So, you know, just plug these programs into the number cruncher, something will come out, and you can often look at the solution, the numerical solution, and guess a lot of the analytical structure.
Absolutely.
And then, you know, you can just, based on that, construct feasible solutions for these programs. And if the value converges to the same number as L goes to infinity, then that's it. You found solutions. So that's what we've done in a lot of cases. Now, it's not always that easy to go from simulations of these programs and then jump to an analytical solution in the limit. And, you know, sometimes, you know, you see like there's some feature of the simulation and you look at it and you say, I would swear that there's a line here, you know, in a linear boundary. And then no, a few months later, it turns out that's not a line. That's, you know, some complicated formula telling you what the boundary is. So, you know, we've sort of gone through twists and turns like that, but that is an approach that one can take.
Mm-hmm. Thank you.
Does that answer your question?
Yes, thank you.
So that's how you would operationalize this. And of course, maybe just from looking at these programs, you can guess analytically what the right solution is. We're not that insightful, I guess. So that's why we resort to, or at least I'm not. Songzi is incredibly insightful, but I just need to go to the number cruncher oftentimes. Okay. So am I supposed to stop at 11? Or
we maybe a minute or two late, that because we started 2 minutes late, but you know, we have a 15-minute Q&A session, so you know, depending what the, you know, how many questions.
10 minutes basically.
Yeah,
10 minutes. Okay, good. So here's the auction problem. Theta, we're now going to make a subset of Rn, and these are value profiles of the bidders in an auction. And theta I, the ith coordinate, is bidder i's value for the good. Okay. And the space of outcomes is a product of an allocation probability where the designer can allocate the good to themselves. I should say there's a single unit of a good, and the designer can allocate the good to themselves or to one of the agents. And then there's a transfer that each agent makes to the designer. And I'm going to write for an outcome, I'm going to decompose an outcome as a Q, allocation probabilities, and a T, which is the transfer to the designer. And then we're going to assume the usual quasi-linear utilities. The designer's objective is to maximize the expected sum of the transfers, and each agent wants to maximize their value times probability of getting the good minus the transfer they make. And then the outside option is just the standard assumption of 0. You know, the agents can walk away and get nothing. So in this case, the bounding programs have this form here, you know, where I've just I've just pushed through this difference in utilities to theta times the difference in the allocation minus the difference in the transfer. So to show that these two programs have approximately the same value when L is large, what we do is start with a QT that's optimal for this problem, and then construct a Q prime T prime that is feasible for this problem that has almost the same value. So that's enough. In fact, we start with a QT that's optimal for this problem. It's not just any QT for this problem. We need to start with the optimal one up here, and then we construct a feasible one down here that has almost the same value. Okay. So one trick is finding the transfer, the T prime. Okay, so we've got a QT and we have to find the Q prime T prime. It turns out that finding the T prime is quite easy, and I'm going to tell you why. So if you look at these programs, T only matters up to this difference, the difference between the sum of the discrete derivatives and the sum of the transfers themselves. Okay, so we're going to call that object the aggregate excess growth. This is equivalently, this is like a discrete divergence of the transfer minus the sum of the transfers. Now we argue in the paper via the Fredholm alternative, basically, so a theorem of the alternative, that for any given choice of this aggregate excess growth, there's a T that solves this equation if and only if the expected aggregate excess growth is 0 under a particular probability distribution, which is an IID censored geometric with an arrival rate of 1/L. Don't worry too much right now about where that comes from, but the point is that there is just this if and only if characterization that, given a C, there's a T that solves this if and only if the expectation of C is 0 under this particular distribution. Okay, and then modulo some subtleties in how we define the discrete derivatives. This is exactly the same condition under which you can find a solution to the counterpart equation for the max G bound, which is this equation here, but with the additional constraint that the lowest type makes a transfer of 0. So this is coming back to participation security. There is a lowest action, and we're going to make that action the participation security action by having the transfer be 0 if that's the action you take. Okay. So in other words, if I start with a T that generates this aggregate excess growth in the upper bound problem, then I know that it must be that the expectation of C is 0. And that condition tells me that I can find another T prime that solves this equation with exactly the same C. And therefore, going back to these programs here, I can use this result to find the T prime so that these terms are exactly the same as these terms. Okay, so that's how we get rid of the transfer. And then for the allocation, the first guess is to kind of shift the allocation so that discrete upward derivatives under Q prime are the same as discrete downward derivatives under Q. And this is the shifted allocation that would achieve that. And this works as long as the Q prime that you get from this shifting operation is a feasible allocation, meaning that the sum of the allocation probabilities sum to less than 1. And the complication is that they will sum to less than 1 if the Q you started with is non-decreasing. But if Q ever was decreasing, then the resulting Q prime from this shifting operation may not be feasible. And in that case, we have to do more work, essentially. And what we do is, well, we show that it's possible. We don't rule out the possibility that the optimal Q for the upper bound problem could be decreasing at some points. But what we show is that it can't jump down. It can't, the discrete downward derivative has to be bounded below. And that's enough to kind of push through this shifting argument, because you can then take this shifted allocation. If there is a violation of feasibility, it's not going to be violated by very much because this change in Q is bounded below. And that means you can just sort of renormalize the shifted allocation in a way that doesn't change the objective very much, but restores feasibility. Okay. So that's how we prove this theorem, that in the auction environment, this last normalization, this last bounding step requires a full support hypothesis on theta over some product set of values. But that's sort of a technical condition. We don't think it's necessary at all, but we don't ever prove. But under that assumption, then we can prove that the bounds are tight for the auction design problem, in the sense that these bounding programs have the same value as L goes to infinity. I only have a couple minutes left, so I'm gonna skip this step of arguing to you that the strategic virtual or the informational virtual objective reduces to the virtual value, and instead I'm gonna skip ahead to showing you a couple of examples. Okay, so here are two examples from the auction environment. One is that so there are two bidders, and they have values that are either 0 or 1. Okay, and in the first case, the values are perfectly correlated. So this is a pure common value setting. Either both bidders have a value of 0 or both have a value of 1. And in the second case, the bidders have exactly the opposite valuations. So they're perfectly negatively correlated. One has a high value and the other has a low value. And both are equally likely. And I'm going to show you the numerical solutions to the bounding programs. And this is sort of coming back to the question that Marzena asked, well, how do you operationalize these bounding programs? Well, one way to do it is by looking at the simulations and then inferring from the simulations, what is the analytical structure. So here is the optimal allocation that you get so this is as a function of the pair of actions of the two bidders, what is the probability that bidder 1 is allocated the good? And it turns out that it has a linear functional form on this range. And then above this cutoff, above this boundary, where the allocation hits 1, actually, then it has the proportional form that I described to you at the beginning of the talk in the introduction. So in particular, your probability of getting the good linearly increases in your action if the sum of the actions is less than some boundary. And then if the sum of the actions is beyond this boundary, which is around 3 in this example, then the good is rationed proportionally. And you can just kind of read that off from the numerical simulation. And similarly, you can read off the form of the worst case information, which looks like this. This is the solution to the dual of the bounding program for the potential. The value is just a function of the sum of the signals. That's what this simulation indicates. And in particular, the value is exponentially increasing. It is an exponential of the sum of the signals. That's this functional form here, when the sum of the signals is below the boundary and then it hits 1. Okay. In a little less detail, this is what the solution looks like for the negative correlation case. It looks like there's, if you take L going to infinity, what it looks like is the allocation is 0 if the probability that bidder 1 gets the good is 0 when x2 is much bigger than x1. It's 1 when x1 is much bigger than x2, and there's some interpolation going on in the middle. In the limit, when L goes to infinity, this interpolation happens very quickly, and it looks like whoever has the higher action gets the good. That's what happens in the limit. And the worst case information actually involves basically no information. So this is depicting the probability that bidder 1 has a high value, conditional on the pair of signals, and it's flat for most of the region, indicating that they don't learn anything from their signals. Okay, so I feel like I'm probably grossly out of time now, so I will stop. And rather than just saying everything that I already said one more time, I'll just stop on this slide that has a list of questions many of which are questions that Marzena already introduced into the discussion. So thank you very much for having me.
Thank you, Ben. Thank you very much. Excellent talk. So we are now moving to the Q&A sessions. We have still quite some time. And traditionally, we'll start with Marzena if there are any questions or comments to kick off the session.
Hi. So I mean, this is a remarkable paper. I'm so excited about these new results. So can you walk us through your and Songzi's thought process or your discovery process? Okay, so once again, I mean, you showed that you can formulate the restricted program at a level of generality that we didn't know was possible until recently. And so what was the key insight? What were the key ingredients in that formulation? I mean, was it thinking about the virtual objective carefully? Was it putting the constraints in the objectives? Can you teach us more?
Good question. So it's been sort of incrementally built up over a sequence of papers, and let's see. So in Songzi's and my, we have a paper that studies common value auctions and doesn't formulate the programs in certainly at this level of generality, but either explicitly, nor does it explicitly formulate them as sort of the guarantee maximization and potential minimization problem. Instead, what we did was we studied those linear programs that I showed you without having a good understanding of why they would be tight, but just as, a way to calculate some candidates. And you might say got lucky, or it was a lucky guess of the right programs. But then once we had the right form of the saddle points, then the way that we were proving that they were a saddle point was basically with this Lagrangian relaxation. It was an argument via weak duality with a particular choice of Lagrange multipliers on equilibrium constraints. So, from the common value, and that's not new really. I mean, that's in the Myersonian analysis as well, right? Where you get, how do you compute the optimal revenue in the independent private value world? You do it by dropping non-local constraints, and then essentially a choice of multipliers, which is that the multiplier on the local constraint is like an inverse hazard rate, which turns out to be the optimal multiplier in the regular case, at least. So, that kind of that particular sort of Lagrangian relaxation was in the mechanism design literature. And what we were doing is kind of finding the dual counterpart to that for the potential minimization problem as well. So in the auction setting, the bounding program for the max G program really is the natural generalization of the Myersonian. It's actually the bounding program for this program, for the bounding program for min potential, is really like a generalization. It's saying, what if you took the Myersonian upper bound on revenue, and then you just minimized over independent private value or independent signal information structures. And then, so that's how we sort of got to that formulation of this dual pair for the auction design problem. And then it was a matter of generalizing from auctions to more general environments. And we had previously done that for bilateral trade as a special case. And for the bilateral trade problem, we sort of just mimicked those steps of saying, let's drop non-local constraints and fix multipliers on the non-local constraint, on the local constraints to get bounds, and then ran with those programs and found solutions. And then this is just a generalization of that methodology where we have just some objective for the designer and arbitrary utilities and outside options for the agents. I don't know if that answers your question, but.
Yes, no, that was very helpful. I mean, I'm happy to ask other questions, but I don't mean to monopolize.
You know,
Please go ahead. If there are other people who want to ask questions, maybe raise your hand so that we know how to manage time.
I would say one other answer to Marzene's question. You know, the particular choice of multipliers seems kind of arbitrary. You know, why are those the right multipliers? And really, you know, this is kind of it doesn't matter actually what you pick for the multipliers, as long as you're picking similar multipliers in these two problems. You know, this particular choice of multipliers is essentially a normalization for the units for actions and messages. You know, because we're saying we're going to normalize the size of a local deviation so that the multiplier on the local deviation ends up being the same. Okay, so the real insight here is not about what is the exact number that you should pick for the multiplier, but just that it should be local constraints. And that is a very classical finding, right? Again, from mechanism design in the 80s, we know how important local deviations are for pinning down information rents and for pinning down the form of the optimal auction. So we're doing that here. We're just focusing on local constraints and then with a normalization for the multiplier. And that's actually something that was in an earlier paper of Songzi's, a solo authored paper, where he uses a similar normalization of Lagrange multipliers to get lower bounds on the performance of mechanisms. They're not optimal, they're not guarantee maximizing mechanisms in this sense, but he still gets sort of good lower bounds when you have common value auctions and a large number of bidders.
So in the meantime, when other people are wondering, let me ask one more question. So I'm really excited about the applied value of your approach as well, right? So not only does it allow us to find the saddle point, but it can potentially help us evaluate the performance of various mechanisms. So have you applied your approach to assess the performance of mechanisms? I mean, you have another paper on posted prices. It's one example that comes to mind, but I was just wondering if you.
Right. So I totally agree with that. That, you know, one way that we're framing this is as a tool to find guarantee maximizing mechanisms. But even if you didn't want to go all the way to guarantee maximizing mechanisms, you know, you could still compute, say, a lower bound on the performance of a mechanism, which is just the expected lowest strategic virtual objective, right? And that's, in a sense, you know, the approach that Songzi took in his paper with mechanisms that are not guarantee maximizing, but nonetheless have a good lower bound on the strategic virtual objective. So, you know, we haven't done that very much yet. You know, we've been mostly focused on getting all the way to the saddle point. But you're right that it's absolutely something that could be done. You know, of course, for a general mechanism, this expected lowest strategic virtual objective is not necessarily a tight lower bound. So a good example would be a first price auction has a disastrous expected lowest strategic virtual objective, but there's a paper of mine with Stephen Morris and Dirk Bergerman that computes a lower bound on expected revenue in first price auctions, which is not disastrous. So meaning that you, just to get the tight lower bound, you have to bring in other constraints than local upward ones.
Mm-hmm. Max, is it okay if I?
So why don't we sort of stop the official part, because we are still recording. I think we can stop the official part of the presentation. So thanks, Ben, for a great presentation, Marzena for paneling, and the audience, Songzi for joining us today, and we'll see each other next week. But meanwhile, I've put the link in the chat. So this is the link to the virtual chair. We'll meet there in a few seconds. You just click on this. The best performance is in the Chrome, we are told. And then you'll pick an avatar and we'll just be walking around, and we'll meet in the seminar room in the virtual chairs. Meanwhile, thank you.